Chapter 7, Section 7 is about exponential growth and decay, and this is a two-part lesson. We're going to start, part 1 is going to be about exponential growth. Okay, that is modeled by the function a times b to the x, just like when we talked about exponential functions last time in our last section, but this time we are talking about something that is growing at an exponential rate. So b, our base here, is called the growth factor, which means that we have to have 1 plus however much change, whatever percent of change expressed as a decimal. Okay, the 1 is the 100% plus whatever percent it's growing on top of that. So a times b to the x is still really what we're doing, but this a times 1 plus that rate of change, or that ratio to the x power, is how you want to plug things in. A is still your initial starting amount. B is your base, which is greater than 1 since it's a growth factor, and x is still your exponent. Okay, we're going to try a couple of these graphs, starting with this first one that says 3 times 2 to the x power. Okay, we're going to throw in our normal -2, -1, 0, 1, and 2. When I plug a -2 in for x, I'm going to get a 0.75, or a 3/4. When I put a -1 in for this x, I'm going to get a 1.5. Plugging a 0 in will give me a 3. Plugging a 1 in will give me a 6, and plugging a 2 in will give me a 12. So now when I go to graph these, I'm going to go back 2, up 3/4, back 1, up 1.5, over 0, up 3, over 1, up 6, and 2 is actually not going to fit on this graph. So now when I try to connect these, you'll be able to see that our graph is going up rapidly, which is why this is called exponential growth. And if you notice, the number that we are multiplying, our base number here, is larger than 1, which should have indicated from the beginning that this was going to be exponential growth. The second one, this 20 times 0.4 all to the x power, I'm going to use my same numbers, -2, -1, 0, 1, and 2. When I plug in my -2 for my x exponent, I will get 125. Plugging in a -1 will give me 50. Plugging in a 0 will give me 20. A 1 will give me 8. And a 2 will give me 3.2. Okay, so now I'm actually going to just mark these as I'm going to count by tens right here. Okay, I can still count by ones on my x-axis. When I graph these, I'm going to have to go back 2, up 125, which is not going to fit on this little graph. But I can go back 1, up 50, and put my dot right there. Over 0, up 20. Over 1, up 8. Over 2, up 3.2. And then when I connect those, I can see that this is not exponential growth. Definitely coming down because this number is smaller than 1. That's actually called exponential decay, and we'll talk about how you find that tomorrow or in part 2. Okay, here's how we might use this. Since 2005, the amount of money spent at restaurants in the United States has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? All right, so we need to fill in what we know. Remember that A is our starting amount. Okay, so our starting amount in this case was $360 billion. Okay, the R is our rate of change, or what it's growing by. This time we know it's growing. So for the R, I'm going to plug in 7%, but as a decimal, that's 0.07. And then our x will be how much this is happening. So they're talking about how much will be spent in 2015. Well, we started in 2005, going to 2015, that's 10 years. All right, so now to solve this, I actually have to put in my numbers. So I'll have y is equal to 360. I'm only going to put that, and we'll just know at the end that it's billion, times 1 plus my growth rate, all to the 10th power. Okay, when I plug all that into my calculator, the order that you want to do that is to start with adding what's in parentheses. So 1 plus 0.07 gives us 1.07. Then you want to raise that to the 10th power. And then, after you have hit equals, you want to multiply that times 360. Okay, so what we got here is 708.174488, and lots of other numbers. But remember now, this is billions, so we actually have to move our decimal so that this says billions. And that tells us that in 2015, the amount of money that's spent on restaurants will be $708 billion. All right, next example. Suppose the population of deer in a region was 3,500 in the year 2000. Since then, the population has grown by 3.5% annually. What will the approximate population be in the year 2020? Okay, so filling out what we know, the first number, the originating number was 3,500. The growth or the rate is 0.35%. When I move my decimal 2 places to the left, I get 0.035. And the x, we're going from the year 2000 to the year 2020. So my x is 20 years. Okay, when I plug it in, I will have y is equal to 3,500 times 1 plus 0.035, all to the 20th power. Okay, so 3,500, I add these together and get 1.035 to the 20th power. Remember to raise that 1.035 to the 20th and then multiply by 3,500. And that will tell us that in 2020, the approximate population of deer will be 6,964.26 deer. Now, you can't have a quarter of a deer, so you could round it if you'd like, but this is just an estimation anyway. Okay, next we're going to learn about compound interest. Compound interest, we've talked about simple interest before, and this one's a little bit extra and actually better if you can find it when you go to the bank. Compound interest is when interest is paid on both the principal, so the amount you put in, and the interest that you've already earned. So every year you're getting your interest on a little bit more of a balance than what you started with. Okay, so our formula for compound interest is A equals P times 1 plus R over N to the NT power. So this is almost the same as our y equals A times B to the X. There's just a little bit more to it. So A is our balance, P is the principal, which is the initial amount or the amount you start with. R is the annual interest rate expressed as a decimal like we were doing before. Now, annual means what percent you pay each year. And then the N is the number of times that interest is compounded per year. And T is time in years. Now, back to this N, the number of times the interest is compounded per year. That's, for example, if they say annual annually, that means one time. They're going to pay you one time each year. If they tell you quarterly, that's 4 times per year. If they tell you semi-annually, that's twice per year. Okay. Let's check this out. Let's try it out, see if it helps. Suppose when your friend was born, your friend's parents deposited $2,000 into an account, paying 4.5% interest compounded quarterly, which we just said would be 4 times. What will the account balance be after 18 years? Okay, so I want you, for all of these problems, to write down P, R, and T, and we're actually going to write down what each of these numbers are. In this case, the P, the principal, the starting amount was $2,000. The interest rate is 4.5%, but we need to change that to a decimal, so we go 2 places to the left, and we know we're going to put in 0.045. The N, if you recall, back here says that's the number of times that they're going to pay per year, and this one is quarterly, so that's 4 times. And then the T is how much time we're talking about, and that says 18 years. Now we can plug it in. A is equal to 2,000 times 1 plus 0.045 over 4, all to the 4 times 18 power. Okay, so this is another one you have to do in order. I would, if I were you, figure out what 4 times 18 is so that you can get your exponent. Okay, and that actually is 72. So I'm going to change this to the 72nd power. Then inside these parentheses, start by dividing this and adding the 1. So if you take 0.045, divide it by 4, and then add 1, you're going to be left with 2,000 times 1.01125, all to the 72nd power. Now it's just like before. So take that number in the parentheses, raise it to the 72nd power, and then multiply it by 2,000. And that tells you that after 18 years, this friend will have $4,475.53. Okay, last example. Michelle invests $8,000, it's your principal, in a money market account that pays 3.25% interest. So when I move that decimal, I get 0.0325. Compounded monthly, there's 12 months in a year. How much will be in the account after 12 years? So we have 2 12s in this one. Plugging it in, I'll have A equals 8,000 times 1 plus 0.0325 over 12, all to the 12 times 12 power. Okay, well, I know that 12 times 12 is 144. And in the parentheses, 0.0325 divided by 12 plus 1 gives me 8,000 times 1.0027 when I round it. Okay, raise that to the 144th power and multiply it by 8,000. That tells me that in that account 12 years later, there will be $11,809.62. All right, that's the end of part 1. You should be able to start your assignment on page 459, numbers 9 through 18, and then also check out your lesson quiz and see what you can do.